All right, let's talk Kafka. If you're building modern software, you've definitely come across it, right? It's this absolute beast of a distributed streaming platform that powers everything from tiny microservices to massive real-time analytics. But here's the thing. Going from a simple Hello World example to a system that's truly production-ready, one that's resilient and secure, well, that's a whole different ballgame. So today, we're going to bridge that gap.
So here's our game plan. We'll kick things off by conquering the common challenges you're pretty much guaranteed to hit. Then, we'll dive deep into mastering fault tolerance so you can build really resilient apps. After that, we'll check out some of Kafka's most powerful use cases. And we'll wrap up by talking about something super important: security.
First up, let's get right into the problems that every single developer runs into when they start using Kafka. And you know what? Don't think of these as failures. They're more like rites of passage for any engineer working with a distributed system this powerful.
Okay, let's start with a classic. How do you handle duplicate messages? See, Kafka's big promise is at least once delivery. Now that's fantastic for durability. You're not going to lose messages, but it comes with a catch. Your application might see the exact same message more than once, especially if there are network hiccups or retries. So the big question is, how do you stop that from causing absolute chaos in your system? The solution is a two-pronged attack, using a concept called idempotency. Now, it's a fancy word, but all it really means is designing your system so that doing the same thing multiple times has the exact same effect as doing it just once. Think of it like pressing an elevator button. Pushing it 10 times doesn't do anything different than pushing it once. The key here is that it's a shared responsibility. On the producer side, Kafka gives you this magic little setting. Just set enable.idempotence to true, and it handles duplicates from retries automatically. But on the consumer side, well, that's on you. Your application code has to be smart enough to handle getting the same message twice. A really common pattern is to use a unique ID from the message to check if you've already processed it before, maybe by looking it up in a database.
All right, next challenge, message ordering. This one trips up so many people. Imagine a user signs up, then they update their profile, then they delete their account. You absolutely have to process those events in that exact order, right? A lot of people just assume Kafka takes care of this globally, but that's a really common and dangerous misunderstanding. Here is the golden rule you have to remember. Kafka only, and I mean only, guarantees message order within a single partition. So the trick to getting all the events for one customer in order is to use a consistent key when you produce the message. For example, if you always use the user ID as the message key, Kafka's internal logic will make sure that all messages for that specific user land in the very same partition. And since order is guaranteed in there, your problem is solved.
So picture this. Your producers are just firing messages into a topic at an insane rate, but your poor consumers are struggling to keep up and are falling further and further behind. This gap is called consumer lag, and if you see that number just climbing and climbing, that's a massive red flag that your application is heading for some serious trouble. So what do?
Here is your playbook for tackling lag. First, you can't fix what you can't measure, so you absolutely have to monitor your lag. The simplest fix is often to just scale out, add more consumer instances to the group. But, and this is a big but, you can never have more consumers in a group than you have partitions. So if you've maxed that out, you might need to increase the number of partitions for your topic. And finally, you got to look in the mirror. Maybe the problem isn't Kafka, maybe it's your code. Profile your application. A slow database call or some clunky logic could be the real bottleneck. You know, this whole idea of scaling consumers and having multiple instances running is the perfect segue to our next topic, fault tolerance. One of the biggest reasons people choose Kafka is because of how gracefully it handles failure. So let's look at how Kafka does this automatically, and how we can build our applications to be even more bulletproof.
So what actually happens when one of your consumer instances just vanishes? Maybe it crashes or the server gets unplugged. Well, this is where Kafka really shines. See, every consumer is constantly sending tiny little "I'm still alive" messages, called heartbeats, back to a central group coordinator. If the coordinator stops receiving those heartbeats for a certain amount of time, it just assumes that consumer is dead. It then kicks the dead consumer out of the group, triggers a rebalance, and reassigns its partitions to the other healthy consumers. They just pick up processing right where the last one left off. No pagers going off in the middle of the night, it's all automatic.
Now, that's awesome for unexpected crashes, but what about a planned shutdown, like when you're doing a deployment? Just letting the session time out is slow and clunky.
The professional way is to do a graceful shutdown. This is where your code explicitly tells the group coordinator, hey, I'm leaving now, which triggers an immediate rebalance. It makes your deployment so much faster and smoother. Pretty much any client library you use will have a close method that handles all this for you.
Okay, this is a much sneakier and more dangerous problem. Your consumer application is running perfectly fine, but it pulls a message that it just cannot process. Maybe it's malformed, maybe some data is missing. Whatever the reason, it throws an error. So it tries again with the same message and fails again and again. This is what we call a poison pill message, and it can bring all processing for an entire partition to a grinding halt.
The solution here is a really powerful pattern that senior engineers lean on heavily, the dead letter queue, or DLQ. Instead of letting a bad message crash your app, you wrap your processing logic in a try-catch block. If an exception happens, you catch it, and then you produce that problematic message to a totally separate dead letter topic where you can look at it later. Then, and this is the most critical part, you commit the offset for the original message. This tells Kafka you're done, allowing your consumer to move on to the next one and keeping the whole system flowing smoothly.
Okay, so now we know how to build these robust, resilient systems. But let's zoom out for a second. Why are we going to all this trouble? It's because Kafka is so much more than just a simple message queue. Let's take a look at the incredible applications it makes possible.
I mean, the versatility here is just incredible. It's the perfect way to decouple your microservices so they can communicate asynchronously. For things like website activity tracking, it can handle a massive fire hose of events in real time. It's also a fantastic central hub for all your logs and metrics from across your entire infrastructure. And then you have the really advanced stuff, like serving as the backbone for stream processing with tools like Flink, or for change data capture, where you're literally streaming every change from your database to other systems.
So, we've built a resilient, high-performance system. We're done, right? Not so fast. This is a critical final step. Out of the box, a Kafka cluster is completely open. I mean, anyone on the network can connect and read or write to any topic they want. We absolutely have to fix that.
Securing Kafka really boils down to three core ideas, or pillars. You've got encryption, which is all about confidentiality. Then there's authentication, which is about verifying identity. And finally, authorization, which is all about permissions.
Pillar number 1, encryption. This is all about making sure nobody can eavesdrop on the data flying back and forth over the network between your applications and your Kafka brokers. The standard way we do this is with SSL/TLS. Yep, the exact same technology that puts that little padlock in your web browser.
So, once the connection is secure and encrypted, we need to figure out who is on the other end. That's authentication. Think of it like a bouncer at a club checking your ID. It's the process of a client proving that it is who it says it is before it's allowed to do anything else.
And Kafka gives you two main ways to do this. You can use SSL/TLS client certificates, which is incredibly secure, but it can be a real headache to create and manage a unique certificate for every single one of your clients. Or you can use a more flexible framework called SASL, which supports things we're all familiar with, like a simple username and password. The one critical thing to remember here is that if you use username and password, you must also use SSL encryption. Otherwise, you're just sending passwords in plain text over the network, and that's a huge security fail. Okay, so we have a secure channel, and we know who the client is. The final pillar is authorization. Now that they're in the club, what are they actually allowed to do? Can this user write to the orders topic? Are they only allowed to read from the payments topic? This is all about defining permissions.
Kafka handles this using something called access control lists, or ACLs, and every single ACL rule follows this one simple structure. A specific user, called a principal, is either allowed or denied to perform some operation from a specific host on a specific resource, like a topic.
Let's break that down with our real example to make it concrete. This ACL right here says that the principal user, Bob, is allowed to perform the write operation, but only from the client IP address 192.168.1.10 on the resource topic orders. With these simple but really powerful rules, you can create incredibly specific, fine-grained permissions to lock down your cluster exactly how you need to.
Wow, okay, we have covered a ton of ground. From handling duplicates in ordering, to building fault-tolerant consumers with dead letter queues, and finally to locking down the entire system with encryption, authentication, and authorization. We've gone all the way from common pitfalls to production-ready patterns. So the final question is for you. When you think about your own applications, which one of these patterns, whether it's idempotency, the DLQ, or security, are you going to implement first?